So now let's consider just the Green's function G for spin polarized system. So this Green's function G in general can be written as spin independent or spin unpolarized Green's function G0 plus the dot product between a spin polarized Green's function G1 and sigma, and the sigma matrix. So actually a task that we will be doing a lot here is to do this. What is the product of two of these Green's functions? So let's say if I want to calculate this, what would I do? Then we will proceed in the following way. So I will say G0 plus G1 dot sigma, G0 plus G1 dot sigma. So then I'll end up with this. Just before Paul mentioned the following, G0 is actually G0 and G1, they have to be matrices of a list the same dimensions of sigma. So then G0 is actually G0 times sigma 0, which is a diagonal matrix. Just keep that in mind, because after all we'll have to take the trace of this GG product, so then this will come in handy. And remember, before we do this, remember that sigma matrices are traceless. So now, keeping this in mind, let's go GG is equal to G0 plus G1 dot sigma times G0 plus G1 dot sigma. This is equal to G0 plus G0 G1 dot sigma. Remember that as sigma is concerned, G0 is a scalar, and the G0 and G1 do not commute in general, so then this is G1 G0 times sigma plus G1 dot sigma G1 dot sigma. So we can proceed with this calculation here downstairs. So then this is G0 plus G0 G1 plus G1 G0. Let's gather this like this, dot sigma. And for this term here, we will use an identity that has been already derived in some of the other videos, which is A dot sigma plus times B dot sigma is equal to A dot B plus I A cross B dot sigma. Use this identity to calculate this. So then, on top of this, we write plus G1 dot G1. This is dot product between the vectors that are been multiplied with sigma, and then plus I G1 cross G1 dot sigma. This is clear that it's 0. So the cross product between two vectors which have the same direction is 0. In this case, they are the same. So then we write finally G0 plus G0, G1 plus G1, G0, all of this dot sigma plus G1 dot G1. So, and if we want to calculate the trace of this quantity Gg, knowing that the sigma matrix is traceless, that means specifically that this term will not contribute to the trace. No trace. But the trace is just G0, G0 plus G1, G1. So this is a quite important result. We need some other results of this sort that we have to derive as well. So for instance, we need to calculate stuff of the sort of G spin operator Sm dot sigma times G spin operator Sn dot sigma equal to G0 plus G1 dot sigma times Sm dot sigma times G0 plus G1 dot sigma plus times Sn dot sigma. So this sort of calculations, and then we need to actually come up with a result for this. So then we will see that actually this, when we calculate the trace of this, we will come up with something, with some, if we sum over M&M, but we don't have the summation index here, the summation notation here, so but if we did have it, it will be some Mn, some stuff Jmn that depends of some product of constants that go next to Sm and goes to Sn, and but the important thing is that this will depend on the dot product between these two. There will be something else, some vector that will dot multiply the cross product of Sm and Sn, and then will be an antisymmetric tensor which will have this form, which we call it I. We should obtain something like this from this calculation, and of course, just I have not specified some constants in this calculation in purple. I actually here I didn't put the summation index, so well, there's a lot of stuff that I didn't do here, though the important point that I want to show you is that this, we have to arrive at something like this from this using a similar procedure than the one we just used upstairs, using something like this and taking into very good account this property that actually I don't even know the name, and I don't even know if in the video I record I call it Pauli's identity. I don't even know if that's the proper name. Pauli's identity. That might not even be the name of that, so I don't know. So then, but that's the idea of working with sigma matrices, and this, of course, the derivation that I just proposed. This, it will be shown in another video. So just this video was just to show you how to work with products of stuff, linear and independent sigma matrices. So stuff of this form. And And actually, this doesn't have to be a vector. It can just be a scalar. So then, yeah. So stuff of this form and what to do with it, and this can be a and c can be 0, and then at those instances, just recall that what you have to use is this identity always. This is very important to recall. Just x dot y plus I x cross y dot sigma. This is a cross product, so you just know. So then at another opportunity, we will come back and see where this comes from, why this type of operations are so important, and we will do some calculations using field theories and functional path integrals. So see you on the next opportunity.